Alright, silly people, here's the situation. This time we're going to be doing a bunch of coding involving the asymmetric quantum well, which is this guy. It has width L and a non-zero potential. And for the actual first part of the problem is to prove that the Schrodinger equation h psi equals e psi implies that you have this sort of relationship between psi m and psi n whenever you're expanding your wave function into a Fourier series like that. So that's what I did first. Oh, the proof is up here. Let me just move this down to the code level. Okay. So yeah, you start with h psi equals e psi. You expand the wave function as a Fourier series. The constant psi sub n times the sine of n pi x over L. You expand it on both sides, noting that you need to use different indexes on both sides. On the left-hand side, you use psi n. On the right-hand side, you use psi m. And then you integrate both sides against psi m times sine of n pi x over L. If you do that, then you have this stuff on the left-hand side and this stuff on the right-hand side. Noticing that you got two factors of psi m on the right side and one on the left side, you can cancel those out. And also on the right-hand side, you can actually do the integral that you're left with because it's just a couple of sine functions with the same m value. So the result of that is L over 2. So on the right-hand side, you have e psi times L over 2. On the left-hand side, you have this. Now this does in fact imply that we can get a matrix form of the Hamiltonian just given by this integral 2 over L times the integral from 0 to L of the sine functions together. And so we were asked to do this analytically for the case of v equals ax over L, which I went ahead and did. H sub mn is going to be given by this. You split up the integral based on the Hamiltonian, so you have a potential term and a kinetic term. The integrals actually have different values based on what m and n are. So I'm just going to proceed through doing the derivatives for the kinetic term until you have an integral of sine functions against another sine function, and on the potential term, you have an integral of x times a couple of sine functions. So the way to do those integrals is explained up here. It is actually that if the m and n match, again, you get L over 2. Otherwise, you get 0. And also here, the integral of x against a couple of sine functions have these three values. Given that you have different conditions between m and n, right? So if you keep in mind those values of the integrals, you can get a h sub mn. If m equals to n, then you get this, h bar squared n squared pi squared over 2ml squared plus a over 2. If m is not equal to n and they match parity, then the element is 0. Otherwise, you get these minus 8a over pi squared mn over m squared minus n squared squared, right? But that's just the analytical part. We also have to do the coding. So what it's going to ask us to do is write a program to calculate HMN for a matrix that is 10 by 10. So a 10 by 10 Hamiltonian pretty much. And figure out what the eigenvalues are, i.e. what are the eigenenergies for this particular square well with the width of 5 angstroms, A of 10 eV, right? So let's do that. I'm going to go ahead and import numpy as np. I am going to eventually plot stuff, so I'm going to go ahead and matplotlib.pyplot as plt. Okay, and we're going to start with n equals 10 for this guy, right? Define some constants. I want h bar. And I'm actually going to leave all of the physical constants in SI units for now, and then convert back to EV at the end. So, so that's 1.055 e to the minus 34 joule seconds for h bar. And then A was 10 eV, but then to convert that to joules, you do this guy, 1.602 times 10 to the 19. The length of the box was 5 angstroms, so 5 e minus 10 meters. And then the mass of the electron given in the problem, 9.1 times 10 to the minus 31, right? Pretty classy stuff. We can initiate the creation of the Hamiltonian matrix. It's going to start out as a numpy zeros object of size n by n with float values that we're going to update in a loop. For m in range n, for n in range n, so pretty standard sort of matrix updating loop. Again, if m is equal to n, then we have a particular analytical value for what the h indexed m comma n should be. It's h bar squared n squared pi squared over 2ml squared. So let's do that. H bar squared times n squared times pi squared divided by 2 times m times, in parentheses, l squared, and then we add on a over 2. Right. In the case where m is not equal to m and one of them is even and one of them is odd, the best way to create that if statement is to just add them up. Say, otherwise, if m plus n mod 2 is not equal to 0, then odd number plus odd number gives you an even number, and so does an even number plus an even number. So if you do n plus m mod 2, you know that's going to be either equal to 0 if it's even, and therefore you want to set that value equal to 0, or it's 1 if it's odd. So I'm just going to have it be not equal to 0. Then you can put in this analytical value for h indexed m comma n, right? And that's going to be minus 8 times a times m times n divided by numpy pi squared times, and I better put this in parentheses, otherwise the feds will get me. But then put this in parentheses. It's going to be m squared minus n squared, right? So that should be good. And I even want to put this in another set of parentheses just to make me feel better about myself. Yeah, that looks good. Okay. Otherwise, it doesn't do anything and it stays a 0 value. So that's cool. At this point, you can solve for the eigenvectors and eigenvalues. I'm going to call it values and vectors equals the numpy linear algebra dot eig with an h on the end there, taking the arguments just h, right? And so we can use that to print out what the eigenvalues are just by running print values. And we'll know that we did it right if it returns the first eigenvalue at around 5.84 electron volts, right? Yeah, 5.84 electron volts, which is why this is not right, because it's returning values in joules. Let me divide by 1.6 e minus 19, 602, whatever. That's still not great. Oh, because I did 10, not 19. My bad. So why am I getting 5 for the first one? It's because for the, uh, yeah, even Mark Newman has a little section about this, uh, that um, the matrix indices in Python start at 0, while the indices in standard algebraic expressions start at 1. And I didn't correct for that, so I need to actually, anywhere that n or m show up, just put +1 in the algebraic expression. So that's going to be also here, +1, and +1, and +1, and +1. Yeah, I wish I could have gotten that right on the first try, but there you go. It's correct now. So the next bit of the problem is to modify it to calculate the eigenvalues with a 100 by 100 array instead of a 10 by 10. That's a very easy thing to do. You can just copy this cell down, put a 0 on here, and let's just have it print the first 10 of those values, right? So we can do :10, because that's the only ones we have to check against. And it looks like, we were already pretty accurate. Increasing to n equals 100 doesn't really change anything at all. The values were pretty accurate to begin with. So that just goes to show how strong my analytical expression is. The next bit of the problem is to also use the code that we have as it is right now to also plot the wave function for the ground state and the first 2 excited states of this potential well, and to pay special attention to the normalization of the wave function, which is a ridiculous thing to say, truly, and I'll explain why in a minute. But to do that, I'm going to create another function in here called psi of n and x, which is going to just return some values for the wave function psi sub n of x, right? Create a value p equals 0. And we're doing this by actually taking the eigenvectors which we have from before and multiplying it in through here to make a sum. It's like a Fourier series of the ground state and the first 2 excited states. So here you do range n, and you say p plus equals the vectors that we got indexed k comma n. So it's the kth value of the eigenvector for a given column n, which represents the given state that you're in. You multiply that by a normalization constant of 2 over L, and also multiply that by NumPy sine. Instead of n in here, you'd use k plus 1, because it's a sum over k times pi times x all over L, right? And at the end, you can just return p, right? We can test this on a list of input values, which I'm just going to call XLS, which is going to be a NumPy linspace, which is going to go from 0 to L in 1,000 steps for that high fidelity graph. At that point, you can plot the XLS versus psi of 0 comma XLS, and also that's just the ground state, right? And I just realized it wants the probability density, not the actual wave function, plotted on there. So just square the function call. That'll return the probability density. So let me grab that, and also uh, do the first excited state and also the second excited state. And when you plot them, they look like this. So the blue is the ground state, right? One hump of energy. The orange guy is the first excited state, so two humps. And then the green guy is the third excited state, second excited state, so three humps. Right, so that's cool. Um, is it properly normalized? No. I really don't know what I'm doing wrong here, but it actually turns out that the normalization of these guys is heavily dependent on how many different sample points you use to do the plot. So if I, for instance, just got rid of the L and divided it by 1,000, which is the proper, uh, which is like the amount of grid points that I'm using to do the plot. Now it would be normalized. This is a normalized plot now. I checked via integration method. So I don't know what the deal is with that. I'm gonna just say that it's a fluke, and this problem is really strange. And I wish that the text in the textbook about it was a little bit better. But you know, it's Mark Newman's textbook. So whatever. Okay.